Alright, welcome to this video. In this video I want to talk about the merge sort algorithm. To do so, I've got some code I'd like to present. This is once again Java code. This is Java code written in my style, which is definitely a peculiar style. Java is not my preferred language. I learned a very long time ago in the C tradition. And so I might have some C-like code here, that might be that. But also today, these days, I code much more using JavaScript as my preferred language, and Python probably my second preferred language. So you might notice I have some style related to that. And then finally, my style. I am a coder that codes primarily for my own research interests, and so because of that, my style is really devoted towards the creation of small functional programs that probably are not going to be maintained by more than a few people. All right, so with that comment on style out of the way, again, I want to reinforce my position on style when it comes to coding. I do not think everyone should follow my style. My style is certainly not the best style. I don't think there is a best style. Rather, there is a best style usually for a particular purpose. So usually you're going to want to determine your own style based on what type of purpose you are coding for. So like I said, I primarily code for myself, so my style has been largely shaped by my own interests. If your code is going to be written for maybe a large community that needs to maintain it, there will probably be community standards that you're going to want to uphold so that your code can be easily maintained by other members of the community. Okay. So again, a few comments on style. I do that because I do now want to take a look at the algorithm and comment on a few of the stylistic choices maybe that I've made that might be different than yours. So to start out, you might notice that the way I've written this merge sort algorithm is not as part of an object necessarily. This is instead just a static procedure that takes a list as an argument. Again, this stylistically is maybe sort of a little bit old-fashioned. It doesn't really embody your standard object-oriented principles, but I'm doing it for simplicity here. So imagine you take a list and you want to sort it. Now the other thing I've done here, and this is largely because I want to have a recursive algorithm here, is I'm also going to have two other arguments, the start and the finish, both integers here, telling me the start and finish index of the list that I want to sort. So of course this could be used programmatically if you only wanted to sort a sub portion of your list, but we're actually going to use this more often than not, as we see here in recursive calls, where we're going to recursively sort sublists as part of our algorithm. Typically, if you're going to have an algorithm like this in your code, you might want to protect your users outside from having to call it on the start and the finish, when default they're going to want to start it on maybe the start index 0 and the finish index size -1. And if that's the case, then you might want to wrap this function. Here I've got it listed as probably being private. I might want to wrap it with a public version that does not have these two arguments, but instead merely calls this version with 0 and n-1 as the standard start. Okay, so assuming maybe that's how we've got it set up, maybe our user just calls merge sort, passes in a list. We call this recursive version of it by passing in the indices 0 and size -1. And now we want to take a look at the algorithm itself. The algorithm is carried out entirely within this if, meaning if we don't jump into this if, nothing happens. So let's just do a quick check here. This is saying if the start is less than the finish, then we do something. Well, let's consider the other cases. What are the other cases? First of all, well, start could be greater than finish. And then, of course, there's the special case where maybe start is equal to finish. So let's consider those couple cases. Well, if start is greater than finish, Remember, this is supposed to be my start index and the finish index. So if start is greater than index, oh sorry, if my start index is greater than my finish index, that probably means that we have an empty list, or this is not a correct argument. We would expect our start to be less than or equal to our finish, not the other way around. So this is selecting out a segment of our array that is negative in size or 0 in size. There's nothing here that we need to sort. So in that situation, we're going to assume this is either an erroneous call or we're just going to terminate, since we're being asked to sort nothing. And if we're being asked to sort nothing, we will do that. We will sort nothing by just terminating. The last special case we should consider is, what if they're equal? If start equals finish, then that's a legal call. Maybe we have a list of size 1, so start is 0 and finish is 0. But again, in that case, that would mean we have a list of size 1, and so we have no reason to actually do anything. A list of size 1 is already sorted, so we can just return. So everything else that we're going to carry out here is going to be carried out if our start is less than our finish, which, let's consider the smallest case there. On our initial case, that might be our start is 0, our finish is 1, so we have a list of size 2. So we actually have a list that is worthy of sorting. So let's look at what happens when we do carry out some operations here. Again, it looks like there's not too much going on. There's 3 method calls, which I'll look at in a little more detail. Before that, we do this one little calculation. Well, here it says I'm going to calculate the midpoint as the start plus the finish divided by 2. And again here, this is going to select out the midpoint. We might want to do some calculation here to see if this is indeed what we would expect. So let's go here. I've made ourselves 2 lists, one of size 7 and one of size 8. Now this is for a couple reasons. One, when I'm testing out my math, my logic here, I want to make sure it works on both even and odd numbers. And then the other reason I've selected these 2 values, one, they're large enough that if I'm going to do some recursion, there's still something being carried out in the next step down. But then secondly, I've selected this size of 8, which is a power of 2, and then 7, which is a power of 2 minus 1, because these both have very interesting and nice properties. A power of 2, of course, if you divide it by 2, gives you another power of 2, okay, all the way down, which is convenient. A power of 2 minus 1, if you divide it by 2 and then take the floor, you'll always get another power of 2 minus 1, which again, so if you get even numbers all the way down on this case, you'll get odd numbers all the way down on this case. So that's actually convenient for us. But the reason I wanted to go over here is we were calculating this mid equals the start plus the finish over 2. So I wanted to calculate, well, which value is actually being picked out here for some value. So let's assume we started with our first list here, where our start here is going to be 0, our finish is 6 over 2, that gives us 3. So yeah, it looks like it actually does pick out the middle element for us. What about in our next case? Again, we're going to get 0 plus 7 over 2. Now, this is going to give us 3.5, but being careful with our math here, we're doing this as an integer division, so that's going to give us actually 3. So again, that's going to select out this element here. Okay, so the one thing we do want to be careful here then, if we want to do our division properly, it looks like this mid element that we've got, we should probably include it in the lower half. If we're using this element to split our list into 2, in the even case, it belongs to the lower half. And then in the odd case, if we allow it to belong to the lower half, that's not going to be a problem. One of our halves has to be larger than the other, so letting it belong to the lower half is not actually going to be a problem for us. So it looks like our calculation here is correct. We can go ahead and calculate that midpoint to be the start plus the finish over 2, as long as on the side that we use, the left-hand side where we go from the start, we include the midpoint. So the left-hand side we're going to merge sort is going to be the start to the mid, and then we're going to merge sort the second half, the mid plus 1, to the finish. So again, let's take a look at what this means for us. That in our diagram here, we're going to split up our list into these two lists here, or in our odd case, into these two lists here, and we're going to recursively sort this list and recursively sort this list. So when we're done, this list will be in ascending order, and this list will be in ascending order. And again, I just want to carry out the same idea or logic for our odd case. We're going to get these two lists in ascending order. Now, at this point in the algorithm, we're trusting in recursion. We're assuming the recursive algorithm is going to work and return back to us what we expect it to return back. But we'll notice now at this point, this is not correct for our output. We need to put them all in order. That's what's correct for our current output. Same thing for this one. We somehow need to take them all and put them in order. And so if we got lucky, if all of these elements happen to be less than all of these elements, then they were already in that order. But more often than not, that's not going to be the case. We need to put some effort into putting them back into order. So in our code, we've merge sorted the left, we've merge sorted the right, but now we need to use some other subroutine, which we're going to call merge, and of course it's up here. I'll look at that in a second. We're going to use merge, and we're going to say merge from start to finish, and that's going to say, hey, take those two lists that we assume are now sorted and put them together, merge them together using, again, another algorithm, one that I've got right up here. So again, what we're saying here is when we say merge from start 0 to finish 7, we're assuming that we have two lists that are already sorted, one that goes from start to mid, the other from mid plus 1 to finish. And the purpose of the merge subroutine is to take them and return the list that's all in sorted order. So we're going to go ahead and take a look at that merge subroutine and see how it works. All right, so the merge subroutine starts out very similarly. We're going to calculate that midpoint. We need it. That's where our first list ends, and then of course mid plus 1 is where our second list begins. So I'm also setting up two counters here. It's going to be a counter that's going to count along the first list, and J, that's going to be a counter that counts along the second list. So again, right here, we'll initialize, say, our I to be pointing here, and our J to be pointing here, mid plus 1. Now these are counters that as we iterate through our two lists, I'm going to either increment I, which will move it through the first list, or J, which will move it through the second list. I'm going to have some temporary storage here that I'm going to use to store the list as I go, but I am going to iterate, as I mentioned, using I to iterate over the first list and J over the second. So this while loop here is going to iterate as long as I is still an index within the first list. As soon as I becomes mid plus 1, it's fallen off the end of the first list. And then likewise for J, as long as J is less than finish plus 1, if it becomes equal to finish plus 1, it falls off the first list. So this loop is the second list. So this loop is going to iterate until one of our indices falls off. So let's see what's going on in this loop. Now this is definitely a line that is indicative of my style. I will use this ternary operator whenever, this question mark colon operator, whenever it seems like it's going to be useful. And when do I think it's going to be useful? I think it's going to be useful when I can save myself a few lines of code. Now, what I'm trying to do with this line of code, let's just say verbally first of all, I want to do a comparison. I want to check to see which is smaller. The element I'm looking at in the first list, so list.getI, that element, or the element that I'm looking at in the second list, element j. Again, what that means here is if when we're starting out, I might be looking at this first location or this location, and I want to know which one is smaller because that's the one that actually should come first in my list. If I'm trying to put them in sorted order, whichever one is the smaller one should be the first one in there. So that's the test. So again, looking at the code, we're going to say here, whichever one is smaller. Now that's the one I want to add into my temporary list. All right, so I really am thinking here, I need some code that looks something like this. If element I is less than element j, then I want to add element I. Else, if in the other case j would be less than I or equal to, then I will want to add element j. Now normally that's going to take us about 5 lines of code in here, and I find that to be a little bit of waste. Not everyone thinks that way, so you probably have heard from someone else that they prefer that way. They probably say, someone else might tell you never ever use the question mark operator. Well, that's not my advice. I think this is a perfect place to use the question mark operator, and in fact on this line of code we've actually got a whole lot of operations being carried out. So let's look very carefully at what this is, reminding ourselves what the question mark operator does for us, and then verifying that okay, this line is doing what we want it to do. So first of all, it looks like what this line is doing is we're adding something to our temp array. Okay, great, we're calling add, which means whatever's inside this bracket, whatever it is, it should be something relevant we can add here. Specifically, it should be an integer. Okay, so let's make sure that this line here, or this expression inside here, evaluates to an integer. Now let's remember what this line actually or what the ternary question mark operator evaluates to. Whatever comes before the question mark, treat that as an expression inside an if. So this should be something that evaluates to a Boolean, a true or false, and certainly it does. This expression evaluates to true or false. If it is true, then the question mark operator will evaluate to whatever comes after it. So if this is true, so if element I is less than element j, then the question mark operator returns this, the element from position I. And then we plus it. Remember, that's going to increment our I and move it to the next element. Otherwise, if this expression is false, then whatever comes after the colon is what's returned by this ternary operator. So as we were looking, the cases that we want, if element I is less than j, we find the element in position I in our list and we add it to the temp. And we increment the counter for that first list. Otherwise, if this is false, meaning they're equal or element j is less than, then we'll take element j and add it into the temp list. And again, use the plus to increment our index. Of course, after doing this a number of times, either our I is going to fall off the end or our j is going to fall off the end. So we want to think about what we want to do in that case. Well, again, looking at our examples here, maybe our I has fallen off the end. If our I has fallen off the end, then it's possible that our j is still, pointing somewhere else. Oops, pointing somewhere else here. It could be pointing, here still. There might be still, maybe these two elements left in our list that we haven't processed yet. But our I has fallen off. Our I is pointing here, so there's no more list left in this one. The other possibility is that our j has gone off the end, and maybe we have a few elements left in our I that we haven't processed. Now, what we'll notice is if there are elements, if we run off the end of our I, if we run out of I and there are still elements left in j here, then those elements are actually in the right spot, because these two elements must be the two largest elements in the whole list, and they're already occupying the location that they belong in. So I'm actually going to ignore that case. I am going to worry about this case when there's still elements left in I. So you'll see my next loop here says, well, what happens if there are still elements left in I? Well, I'm going to just go and copy those elements into my temp list as well. So now there won't be any elements left in I. All right, so again, going back to our example here, that means now if there were elements left in I, now I've copied them into the temp list. So that means we're either going to be in the case where we have a few elements left in J, but they're in the right location, or we had run off J first, so there are no elements left in J, and now we've also emptied the elements out of I. So our temp array is going to be completely sorted with either all the elements of our whole list, or all the elements, up to this point, if there were still a couple elements left in J that we haven't emptied out. All right, but in either case, we're ready now to overwrite our array with the temp array. So the last loop that I have here just goes and copies the elements from the temp array over the elements in the list. So overwrites those elements. So at the end, our list will now have all the elements that it originally had, but now in sorted order, at least for the elements between start and finish, and at least assuming that the input assumption was made properly, that those two subarrays were already already sorted in ascending order. Okay, there might be one last thing I want to comment on related to the correctness of the algorithm, or how the algorithm operates. And for that, I wanted to maybe look more closely at the odd case and see, does anything really change in the odd case when we're merging our two lists together? And luckily what we'll notice is nothing hinged on our two lists being the same size. And in fact, this is probably very clear. Say the first thing that happened is we moved our I to this location. So maybe after our first step, we eliminated this element. If we've done that, then we've now created an instance where we have two lists of different length. This one's of length 3 and this one's of length 4. But the next step still works fine. We might even still pull this one out again in the next step, advancing here. And it's possible that we could actually empty all of I before even getting to an element of J, and the merge operation is going to work completely fine doing that. So there's nothing different in the even case and the odd case. We verified that our midpoint math picked out the right element, and we're including that in the lower half, so everything should work out fine in the odd case, just as it did in the even case. We've taken a look at the algorithm and how it operates, but now I want to take a look at the actual runtime, how many operations are carried out by the code. And to do that, we actually need to use some mathematical techniques a little bit beyond what we've been looking at so far, a little bit beyond the summation work that we looked at for the first couple algorithms. And my purpose today is to share the analysis so that we can be comfortable following it, being aware of how it operates, but maybe not able to reproduce a similar analysis for some other code that we might encounter. I will create another video in a different series that has a more detailed analysis of merge sort than this, which, if you're interested in, stay tuned for, and you can take a look at the more detailed analysis. I am actually going to do a portion of that analysis right now using a technique called Recursion Trees. And to do that, what we're basically going to do is we're going to build the recursion tree for the recursive algorithm. And what does that mean? Well, it means something like this. Imagine we're on the first level here. This is a node I've drawn here. And when I say I'm on the first level, I'm going to maybe start keeping track of some stats here. So let's make that an L. Let's say this is level 0. Okay, and on the level, I'm going to keep track of a few things. One thing I might keep track of, what is the size of nodes on this level? And so on the very first level, when I make a recursive call to my merge sort, the size of my list is n. And then the other thing I might want to keep track of, at least for the moment, is I want to keep track of the number of nodes that there are on that level. And well, on the first level there are 1. Now the next level down, I'm going to try and draw my levels as I go here, at least until it becomes cumbersome. We know that the recursive call for merge sort is going to split my list into 2, and it makes 2 recursive calls. So again, I'm going to call this level 1. And on the next level down, the size of my array has shrunk. Now, here's where I guess I can make some choices. And the choice that I'm going to make right now is I'm going to assume that my original size here, n, is even. And actually, I'm going to go a little further than that. I'm going to assume it's a power of 2. So now I'm going to write n over 2. That way I know that when I divide my list in 2 here, remember the case for 8, every time we go down we'll get another power of 2, we'll get another even number. We'll always get something that evenly divides on the way down. That's just going to make our math easy for the moment and maybe help us in our analysis. How many are there going to be on this level? Well, I've drawn it out here. There's 2 on this level. And really, the recursion tree method is just going to try and continue this until we see a pattern. So here on my next level down, I tried to draw my tree, not a very great tree here. I try and draw a tree. Next level down, we're on level 2 now. I've sort of strategically started drawing at level 0. We'll see the math's going to work out in a second. And on this level, we now have n over 2, but divided by 2 again, n over 4. How many nodes on this level? We can see here there are 4. So I'm trying to get a pattern here. Hopefully after this level we'll see the pattern so I don't have to draw anymore. But the next level down here, again I'm going to call this level 3. How many nodes do we have down here? Oh, we now have 8 of them. And we'll see the math works out here too. The size now, n over 4 divided by 2, will be n over 8. We're getting these powers of 2 showing up in our calculation. And hopefully if we see that, we might say, okay, dot, dot, dot here. There's some level down here. I'm going to call it level I, somewhere in the middle. And we can maybe think, okay, how many nodes would there be on that level? Well, on this level, this level 0, there was 2 to the 0, 1. On level 1, there was 2 to the 1, there was 2. So I'm going to say, well, this is probably 2 to the I on this level. And it looks like the size on that level would be 2 to the I as well. Now, we're going to continue that, dot, 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 all the way down here. We're going to arrive at some level, and I'm kind of drawing this with squares here. This is going to be the bottom level, the terminating level, where maybe every recursive call on this level has size less than or equal to 1. Specifically, since I assumed my n is going to be a power of 2, that would be exactly equal to 1. But in some cases, if we didn't have a power of 2 here, some might be terminating with size 0, some might be terminating with size 1. But we're down at the terminating calls here. At the moment, I don't know what level that is. I'm going to have to figure that out in a second. But I'm going to call it level k for now. And using the math I've got here, I can probably say, well, then there would be, the size here would be n over 2 to the k. But I've just said, I want this to be a case where n over 2 to the k is 1. We've got to the terminating level where all of our terms have got down to the terminating case of size 1. Remember, in merge sort, that case of size 1, we just return, we don't do anything. And again, the number of elements on that level, the number of terminating cases, we should expect to be 2 to the k. Again, we haven't said what k is yet, but we can probably use this formula here to solve for it. Now, I was mentioning we wanted to use this recursive tree. This is I've sort of drawn out here the recursive tree. This is actually this is a depiction of the operations that are carried out by the algorithm. And in fact, let's take a moment to refresh our memory of recursion. Let's think about the actual sequence of operations that will be carried out. The code that we have here, maybe I'll bring it back. The first thing we're going to do is we're going to make a a merge sort call to the left. Now that's a recursive call, which means we're going to jump back in here, and that's going to make a recursive call as well. So actually, the path that we go here, we might think that what happens is the root call first makes this call and then makes this call. That's not actually true, because this call interrupts. It passes its flow of control down to this node now, and this one makes a recursive call to the left. And then this one makes a recursive call to the left, and this goes all the way down until we get all the way to the bottom where we get this one, which finally this one returns back up and says, all right, I'm done. I'm actually already sorted. And we get actually the next recursive call is this one here. And we get this sort of trickling back up and backtracking up and forth, up and forth, up and forth, until the whole left side is actually sorted. And only then do we recurse down the right-hand side. Okay. Now, we don't need to worry about that order. What we really need to worry about is just the cost of all these calls. It doesn't matter what order we go through them. What matters is the cost of all of them. So I'm actually going to add something to my calculation here. I'm going to add a few more calculations. I'm going to have my cost per node, okay, or call. And then here I'm going to have my total. Or maybe I'll just say total cost to be very clear. Okay, didn't leave a lot of room here, but on my first level, if I want to know what the cost per node is, well, here I actually need to think a little bit carefully. How much work do I do? And again, let's maybe jump back fully to the code here. How much work do I actually do in addition to the recursive call? So I want to just sort of stare at this algorithm here and see how much work am I doing. When I get down and analyze the next level down, I'll take care of the operations carried out by these two calls. But how much work is being carried out elsewise? Well, there's obviously some constant amount of work being carried out to do the arithmetic, and I might check here. There's some arithmetic here as well. But then the bulk of the work is actually carried out by this merge algorithm here. And the merge algorithm is actually going to take some linear amount of steps. And linear here I mean big O of n, order n steps. And that makes sense. To merge my two lists, I need to copy them over, so I have to look at all those elements, and that takes me at least order n time. So in our analysis, adding that to our analysis, we want to say here, how much does it cost me on each call? Well, each call, I have to spend a linear amount of work. Now, my instinct might be to write something like n here. That's not exactly correct because there's some constant out front that I don't know what it is. So I'm going to call it c, just to be careful here. So the cost on that level is Cn. The next level down, we still have that linear amount of work carried out, but keeping in mind that we're actually only half the size now. So we actually get Cn over 2 here. And then likewise, as we keep going, C times n over 4, C times n over 8, and then in general, C times n over 2 to the I. Now, when we get to the bottom level, the terminating condition is going to be something completely different. We no longer do the recursive call. Again, looking at our code here, in the terminating condition, we just do that one check, and then we actually terminate. Now, I might put 1 here. It might only be one operation, but again, I'm not really confident in that, so I'm gonna make a D. Okay, give it another name, D. So to complete my calculation, I have to figure out the values in my final row here, but that's pretty straightforward. It's just we're multiplying the number by the cost, and we'll see here this one's pretty easy. It's C times n. We'll also notice here the 2 and the 2 cancel out. We get C times n again, and we see, yeah, that pattern continues here. Every level, the cost of each level is actually the same. And that works for some of our algorithms, not all of them, but it worked on this one. And then the last level, that one's maybe the different one. We get d times 2 to the k. Okay, so we need to figure that one out. All right, we get to put this all together now by realizing that the sum, the number of operations carried out by the whole tree, is actually the number of operations carried out by this column. So we need to just add all these together, add them all up. So I'm going to write that down here, and this is where our summation math is going to come back and help us now. I'm actually going to write this term first. This is all by itself. So this is my d times 2 to the k term, plus all these other terms which I can write as a sum. I equals, now here, luckily the math that I've done here, I've got my I, that's the term I want to sum, and it starts here at 0, so I can see that, and it actually ends at k minus 1. We go up to the last level but not including the last level, so k minus 1. Now what's the cost on level I, on each level? It actually is this here. It's just c times n. We saw that already. Every level costs the same. So we can kind of simplify that. This is a very simple one to see. We still have our our d times 2 to the k plus then this sum here, 0 to k minus 1 must be k times, remember the c and the n don't depend on the I, so I'm factoring them out, and that gives me a copy of k here. That's going to give me c times n times k. Okay, c times n times k, whatever k is. And that, I guess, brings us to the question, well, what is k then? We need to figure out what k is. And the only way to do this is to take this equation right here and use it and solve it. So let's do that. So we're going to have n over 2 to the k is equal to 1. Multiplying both sides by 2 to the k gives us n must be equal to 2 to the k, right? And then taking that one step further, we're going to take the log of each side. We're going to go log base 2 of n must be equal to k. Okay, and remember I assumed n was a power of 2, so this is fine. This all works out. This is k. So it looks like on the value that we end up here, our k, we're going to get d times 2 to the log base 2 of n. That should be an easy one to calculate. Plus c times n times log base 2 of n. And we'll see this one, these cancel out and just give me an n. So, well, let me get myself a little more space here. So, all in total, we get d times n, that's my first term, plus my cn log n term. Well, that's the dominant term. Multiplying the n by log n makes it bigger, so this one's smaller. So we get big O of n log n. I'll maybe just comment one last thing about a little shorthand here. LG is the computer science shorthand for log base 2. Okay, and that's similar to the calculus shorthand of ln for log base e. Okay, so you might see that a couple times. I'll do that, usually just to save myself an O, but there we go. We've done some analysis here to show that our merge sort algorithm is indeed a n log n algorithm. And we've done that by taking a look at the recursion tree method. Now, as I mentioned in my series on algorithm analysis, I will post a more detailed analysis showing more examples of the recursion tree method, as well as showing ways that we can prove that this bound is true. So we've done some math here, but how do we prove that it's true? So stay tuned for that if you're interested in those details. If not, my next video, we're going to take a look at our final sorting algorithm in this series, the quicksort algorithm, also an n log n algorithm, and again, I may include a small amount of analysis in that video. All right, thanks for watching, and we'll see you in the next video.